Let's look at wave characteristics. So we just finished talking about simple harmonic oscillators, and there's a direct connection, of course, between simple harmonic oscillators and waves. Here I've got an oscillator, and because there's some movement behind it, the paper behind it is moving, what gets traced out is a waveform. So of course, a lot of our definitions are going to transfer from oscillatory motion to wave motion. So for instance, our amplitude used to be from the equilibrium point to the point of maximum displacement. Now we've got a whole line, which we could call the equilibrium line or equilibrium axis, and we can talk about the amplitude being the distance from the equilibrium axis to the point of maximum displacement. And we're going to have a new quantity now called the wavelength. It's going to be very connected to the frequency in the period. When this oscillator goes through one complete cycle, to and then fro, what's going to be traced out here is going to be a down and then an up. And the distance that gets traced out there, we're going to call that the wavelength. We're going to be able to define it in different ways. One of the ways is to say it's the distance between one crest and the adjacent crest, where the crests are the peaks of the waves. Let's go through several of the definitions. We'll start with the wavelength, and we just said that that was the distance between adjacent crests. But a more general way of defining it is to say it's the distance between adjacent points with the same phase angle, or just the same phase. Let me show you that. The oscillator is fixed, and here it's connected to a string of beads so that we can see the individual points on that wave. And the first thing that's quite interesting is that any of these beads is just executing simple harmonic motion. So they're all executing exactly the same simple harmonic motion, but they're just slightly out of phase with each other. And if I consider this point here, that green point, and this point way over here, you notice that those two are doing exactly the same thing, that I can kind of follow both of them at the same time. They go up, they come down. They go up, they come down, etc. And we'd say that those 2 points were in phase because they're doing exactly the same thing. So they have the same phase angle. And we say that they're adjacent to each other, meaning that they're the two points that are closest to each other that have the same phase. We could also have other points in phase that would be 2 wavelengths along or 3 wavelengths along. So a good definition, general definition for the wavelength is the distance between adjacent points with the same phase angle. Now, period, when we talked about simple harmonic motion, was the time for one cycle. We can also define it as now as the time for the one wavelength to pass a point. In other words, if I go back to when my oscillator goes through one complete cycle, in that time, you'll notice the wave, let's trace it out here. The wave, I'll go out to the crest. The crest gets to here. So that wave, that crest, passed through exactly one wavelength when the oscillator went through one cycle. So we can say that the period is the time for one wavelength to pass a point. Frequency, well, it's cycles per second, but now we can define it in terms of the wavelength because it's the number of wavelengths that would pass a point each second. The amplitude, we already talked about that, the distance from equilibrium to position of maximum displacement. And a new term, the medium, that's just whatever the wave travels through, whether that be water, a spring, air, whatever it may be. When we start graphing this motion, there's basically 2 different types of graphs that we consider. There's displacement versus time graphs and displacement versus position graphs. So this first graph here, this is displacement versus position. And it would be like if you take a photograph. Because in a photograph, you freeze time. You're taking that photograph at an instant of time. And this is what the photograph would look like. The displacement versus time graph, it's like focusing in on one of those beads that was oscillating up and down. Your focus on one point. And remember, each of those points was like a simple harmonic oscillator. So you're basically you're doing a graph of a simple harmonic oscillator. You're focusing in on one position. This is at one position. Whereas this one here is at one time, at one instant in time. We now come to the universal wave equation. It's really just our equation, speed equals distance over time, but we're going to kind of use new variables because now we're dealing with waves. And so we use a lambda symbol, that's the wavelength. This is the Greek letter lambda. And of course, we call it a length because it's a distance. It'll be in meters. And the other common variable that we use is the frequency, which of course has units of hertz or cycles per second or seconds to the -1, etc. Now, what I can do here is I can say speed equals distance over time. But I can choose a particular distance. And the particular distance that I'm going to choose is the wavelength. I know the speed of a wave is constant as long as I don't change the medium. And I'm going to talk more about that in a second. But for right now, I'm going to choose my distance to be one wavelength. Now, if I do that, then by definition, the amount of time it takes to travel one wavelength, that's called the period, t. And of course, t is equal to 1 over f, or f equals 1 over t. So I can replace that 1 over t by an f. And I'll get my universal wave equation, v equals lambda f. And that's really useful. If, say, I wanted to find out the wavelength of the radio waves coming from a certain channel that was located at 100 megahertz on my dial, then I could say, okay, well, v equals f times lambda. Therefore, lambda is equal to v over f. My speed is 3 times 10 to the 8th meters per second. That's the speed of light. It's the speed that all electromagnetic waves travel at in a vacuum. So we've got 3 times 10 to the 8th meters per second. I'm going to divide that by the frequency, which is going to be 100. Mega means a million, or times 10 to the 6th. And that'll be per second. So this is really 3 times 10 to the 8th divided by 1 times 10 to the 8th. And I'm going to get an answer here of 3 meters. So the wavelength of those waves, of those radio waves, would be 3 meters. Okay. The second example here, it's really a preview into what's coming up in a second. I'd like you to try the question, then come back for the answer. Okay, part A, I'm expecting that your thinking went something like this. You'd say, okay, we got these bullets traveling along at 300 meters per second, and the amount of time between firing, well, it's 10 rounds per second, so that means it's going to be 1 over 10, or 0.1 seconds between firings, and then you'd say that distance equals speed times time. So you're moving at 300 meters per second, and you get to move at that speed for 0.1 seconds. So you're going to get a distance between the bullets of 30 meters here. So this will end up being 30 meters. And in part B, hopefully you said that if you increase the rate at which you fire, then this time is going to drop, and that means the distance between the bullets will decrease. So it'd still be moving at 300 meters per second. That wouldn't change. But this distance between them is going to be less. Now, what does this have to do with waves? Well, we're going to look at how do we change the speed of a wave. It turns out you can only affect the medium. And so in fact, as you kind of increase the frequency of a wave, you decrease the wavelength. So in this case here, we can kind of think of this as there being a wavelength here. So when we increase the frequency, we got a shorter wavelength. Let's see that in more detail. Okay, so there's only one way to change the speed of the wave. And in one way or another, you're going to have to affect the medium. You're going to have to affect the air or the glass or the water, whatever that wave is traveling through. If you try to change the frequency or the wavelength, you'll find that as you increase the frequency, so let's say that we had a really high frequency. If we tried to increase our frequency a lot, what happens is the wavelength drops down a lot and the speed doesn't change. Or if you drop the frequency really low and the wavelength gets really long and you end up with the same speed. So we can kind of draw that. If you have a really high frequency, you get a short wavelength. If you have a low frequency, you get a long wavelength. And the product is going to always be the same. So if you've got a slinky and you try to create a wave in that, you can't shake your hand more quickly. You can't even create a larger amplitude wave. A larger amplitude wave won't go any faster either. So I might mention that larger amplitude does not affect speed. So maybe try this. How could you change the speed of the following types of waves? So let's start with a sound wave. You might know that the speed of sound is given by 332 meters per second plus 0.6 T, where that temperature is in Celsius. In other words, if I change temperature, if I increase temperature, my sound will travel more quickly. And in fact, sound travels much more quickly in water than it does in air and travels much more efficiently, so that if you team up with a partner and your partner goes maybe 100 meters down the beach but underwater, and you both go underwater and one of you taps some rocks together, that sound will travel really well through the water and you'll hear the rocks hit together much more loudly than you would really want to. Same thing with railway tracks. That's steel. Sound travels even better through that, and that's why you can hear a train coming from such a long distance if you bend your ear to the track. In the Three Stooges movies, when they put that steel bucket on one of the other Stooges' head and then rattle that with a hammer, that's something you don't want to try at home because that really will cause some ear damage. Light waves, well, light can travel all the way from the sun to here without any medium at all. So light's the only thing that can travel without a medium. But when it is traveling through a medium, we can affect that medium. We can, light will travel more quickly through warm air than cool air. Light will also travel much more quickly through air than it does through water. Water, how could you change the medium if the medium's water? Well, you can change the depth of the waves. The speed of water waves will change with depth. That's why you get all this capsizing that goes on when the waves come into shore. They're moving along and suddenly they hit a shallow sandbar, and the top of the waves has lots of momentum, and the bottom of the wave slows because of that decreased depth. And so, of course, the top of the wave will cascade over and create a white cap. That always occurs on the sandbars. And for a slinky, the best way to change the speed of waves in a slinky is to stretch the slinky more. Change the medium that way. It's a very good thing the speed of sound waves is not affected by the frequency. Otherwise, you could go to a concert. You're sitting back here at the concert. There's a bass producing a low frequency, and then maybe you've got a little violin here, and it's producing a high frequency. Well, let's say the high frequency traveled more quickly. The sound from the violin is going to reach you before the sound from the bass. And so all the sounds are going to be totally out of sync with each other, and it's going to sound chaotic. Which comes first? So here's our universal wave equation. So we kind of got to decide what determines what. Well, the frequency is always determined by the frequency of the oscillator that's creating the motion. So it kind of is the most fundamental. Always determined by frequency of oscillator creating wave. So for instance, if you have 10 slinkies together, and they're all different types of slinky, and you generate a wave by moving your hand up and down at a certain frequency, then you'll find that the frequency stays the same no matter how many different sections of slinky you go through. The frequency doesn't change. So this is kind of what comes first. Then, of course, the speed will be determined by the medium. And then once you've got those two, this one falls into place. A very common IB question is like the one that is up on the board now. Maybe try the question and then come back for the answer. Okay, so a wave travels from one medium to another, so we are expecting a speed change. And which of the following are true about its frequency and wavelength? Frequency, no change, because that's always determined by the frequency of the source. The wavelength will change. So your correct answer should be C. So when we write V equals F lambda, that one was from the source, and that doesn't change at all. This, it did get changed because it was a different medium, and the wavelength just follows suit. So that if I, say, went to a medium where the waves were faster, then the wavelengths would be longer. And one last little topic, transverse and longitudinal waves. You've probably created longitudinal and transverse waves in slinkies. So if you oscillate back and forth along the slinky, you get a longitudinal wave. So longitudinal, you want to think along, vibrations along. Transverse wave, of course, you vibrate your hand up and down. Transverse really means perpendicular to the slinky itself. Let's look in more detail at the transverse wave. So here's a transverse waveform. If I focus in on any one of those particles, you notice that it's just oscillating up and down in simple harmonic motion. So you've got oscillations that are up and down, but the actual movement of the wave, so if I try to follow a crest along here, so I'm going to try to get in sync with a crest and move across. So my motion of a crest is perpendicular or transverse to the vibrations of the particles. And that's the key feature. That's the key feature of a transverse wave. The vibrations of particles. If you've got a slinky, that would mean an individual coil on the slinky. The vibrations of the particles are transverse, which means perpendicular, to the motion of the wave. Names of the parts. We call the top part, we call that a crest, and we call the bottom part, we call that a trough. Key examples of transverse waves include light and water waves. Although we'll see later that water waves are actually kind of a little bit of both. And then for a longitudinal wave, we no longer get crests and troughs, we get compressions and rarefactions. So this example of a sound wave, you've got air molecules that are close together here in a compression, and then they're farther apart in a rarefaction. And those, you can see here that those compressions, they move along. So that's the motion of the wave. So the oscillations, you can see very clearly focusing in on that red particle. that it is doing simple harmonic motion about an equilibrium point. So its oscillations are in this direction. And the motion of the compressions, this is moving quite slowly, the motion is in this direction. So the key feature, the motion of wave, so the key feature is that the vibrations of particles are along the motion of the wave. The names of the parts, so we no longer call them crests and troughs, we call them compressions and rarefactions. Most common example would be a sound wave. Of course, with a slinky we can generate both longitudinal and transverse waves. Turns out a water wave, the particles actually do kind of a circular motion. And I did see one IB question where they took this into account. So I did kind of want to point that out. But remember, circular motion, a circular motion really corresponds to vibrations in two directions. You've got vibrations vertically and vibrations horizontally. So it's kind of combining both longitudinal waves and transverse waves. And you notice that the waves don't extend very far either. So water waves are actually fairly complex. And that's all for today, folks. Thank you very much.